Welcome to The Explainer. We're all dreaming of the day we can have a robot that just gets us, one that understands what we say and can actually help out. Well, today we're going to break down the recipe for building a robot brain that can do exactly that. I mean, think about it. You tell it to open the oven, and it opens the oven. Sounds simple, doesn't it? But bridging that gap, between understanding a command and then making all the right physical moves, that is one of the huge challenges in robotics. So today we're diving deep into creating these generalist, do-anything robots that can actually follow our instructions out in the real world. To get to the bottom of this, we're going to follow the exact same investigative path laid out in a groundbreaking new research paper. We're going to answer the key questions that, piece by piece, unlock the recipe for building much, much smarter robots. All right, let's get right into it. The first step is to really wrap our heads around the core technology that connects seeing, understanding, and most importantly, doing. And that technology is called a Vision Language Action Model, or VLA for short. Now, here's the crucial idea. You don't build these robot brains from scratch. Instead, you take a super smart AI that already understands images and text, and you essentially give it a body to control. You're teaching an existing, powerful brain how to move. So, the big question is this approach actually any good? Do these VLA models really deliver? Well, researchers put them to the test to find out if this whole idea pays off. They used a really tough simulation called Calvin. You can think of it like a brutal obstacle course for robot AI to see how their new VLA model, which they called RoboVLM, stacked up. And the results? They were pretty striking. It didn't just win, it blew right past the competition, even outperforming other VLA-based models. I mean, just look at that gap. We're not talking about a tiny improvement here. On average, their new RoboVLM could nail almost 4.5 complex tasks in a row. That's a new high score for this incredibly difficult test. And this brought the researchers to their first major takeaway. All the data points to one thing. Building on top of these powerful, pre-trained vision language models is an incredibly effective strategy. It's a promising path because it gives the robot a massive head start in understanding the world around it. And get this wasn't just happening in a clean, perfect computer simulation. When they brought it into the real world, the model was so robust that it started doing something amazing. It began correcting its own mistakes. Like if it fumbled grabbing a handle, it would just try again, all on its own. Nobody explicitly trained it to do that. That's a huge step forward. Okay, so we know VLAs work. The next logical question is, what's the best way to actually build one? What's the right blueprint for the architecture? All right, first decision. How does the robot move? Do you give it a limited set of options, like move a little bit left, turn a bit right? That's called discrete actions. Or do you give it smooth, precise control, like a joystick? That's continuous. And it turns out, precision is king. Continuous actions won, hands down, especially for longer tasks, where tiny little errors can pile up and cause a failure. Next up, does the robot need a memory? Should it remember what it just saw and did? The answer is a huge, definitive yes. Models that could look at a history of their past actions and observations performed so much better than ones that only saw the current moment. Context is absolutely crucial. So the winning formula becomes clear. You want a robot brain that remembers the past and acts with precision. The best way to wire this up is with a special component called a policy head. You can think of it as the central decision maker that takes in all that history, fuses it with what's happening right now, and then outputs a smart, smooth, continuous action. But remember, this whole VLA is built on top of a pre-existing foundation model, a backbone. So that leads us to our next big question. Which one should you pick? Which foundation works best? The research team put a whole slate of them to the test, 8 different backbone models. And as you can see from the results, 2 clearly rose to the top of the pack, Cosmos and Pelagemma. They just consistently performed better. So what does this tell us? It tells us that the quality of your foundation matters immensely. It's not just about picking the biggest model. The ones that performed the best were the ones that had already gone through massive pre-training, learning that deep connection between images and language. That's the real head start. Okay, so we've got our architecture and we've picked the right backbone. But how do we actually use robot-specific data to teach it how to do its job? What's the best training strategy? The researchers tested out 3 different recipes. The first was to just throw all the data, general robot data and specialized data, into one big pot and train it all at once. The second was to only use the specialized data for that one robot. And the third was a 2-step approach. First, pre-train on the general stuff, and then fine-tune on the specific stuff.
And the results showed a very clear winner. That 2-step process, what they call post-training, where the model learns general skills and then specializes, was the most effective. It gave them the best overall success rate at 52%.
So the best recipe is to start broad and then specialize. This approach gives the model a really robust foundation for what it even means to be a robot. And then it adds that targeted expertise it needs for its specific body and its specific environment. It's really the best of both worlds. All right, let's put all these pieces together and look at the final recipe for building one of these high-performing, do-anything robot brains. It really comes down to answering these 4 simple questions. Why do this? Because the VLA approach is effective and efficient. How should you build it? With a policy head that remembers the past and acts with precision. Which backbone? A strong, well-trained one like Cosmos or Polygamma. And when do you add data? Using that 2-step post-training strategy. By answering these, the researchers have given us a clear roadmap. And maybe the best part of all this is that they didn't just keep this recipe to themselves. They released a whole open source framework called RoboVLMs. This gives the entire robotics community the tools to easily build, test, and deploy these models so we can all push the field forward together. So what this research gives us is an incredibly powerful blueprint that takes a lot of the trial and error out of the process. And that leaves us with a very exciting question, doesn't it? Now that we have a much clearer recipe for building smarter, more capable robots, what should we build next? What new challenges can we finally tackle?